Hello, everybody. It is Monday, January 5th, 2026, 12:32 a.m. And I'm here to explain the Monty Hall problem for you guys in a couple of different ways that are going to make it clear how you can think of this problem logically, mathematically, and intuitively. And so the basic overview of the problem, I'm going to assume you already understand what the problem is, but just a refresher. There are three doors. It's a game show, right? Three doors. One of them has a car behind it or some other valuable prize. Two have goats behind them. And whatever door you pick, the game show host opens one of the other two doors. And there's a goat behind that door, and he asks you if you would like to switch. So the question is, do you switch? And most people intuitively believe that, well, it should be 50-50. Shouldn't it? It doesn't matter if I switch or not. It's just, mind games and mind tricks. Well, it's actually 67% to 33%, right? 67% says you should switch, right? You get double the chance to win if you switch. Now, let's see if we can prove that very simply with the easiest way to break down this problem, which is to count the cases. And so what does that mean? Well, it's very simple. You count how many cases exist in which you win if you switch, and you count how many cases exist in which you lose if you switch. So let's say case number one is that the car is behind door number one. And say you pick door number one, right? Now the game show host can either eliminate two or three, doesn't matter, right? And either way, you will lose if you switch. So that's one case in which you lose if you switch. Now, quickly, you can see, well, if you pick door number two, well, they have to get rid of door number three for you, and so you'll win if you switch. Similarly, if you pick door number three, well, they have to get rid of door number two, so you'll also win if you switch. Now, I'll do a couple more, but you guys should see the gist here pretty quickly, right? Now, we move the car to door number two. Okay, well, say once again, you pick door number one. Well, they have to eliminate door number three, and you win if you switch. Now, if you pick door number two, right, they can eliminate three or one. Say they eliminate three, right? You lose if you switch. Now, if you choose door number three, they have to eliminate door number one, and you win if you switch, right? So either way, there's 2 times as many cases that you win if you switch, which makes sense because you have a 67% chance of winning, or we're going to do 66.6 repeating percent, right? Chance that you win if you switch, right? Now, the last set of cases that we're missing is if the car is behind door number three, and we can add 2 there, add 1 there. So the answer is correct as far as I can tell, but here's the problem, right? How do I actually think of it logically? Well, this is my favorite way of doing that, which is to break it down into 2 different blocks. What do I mean by that? Well, say we have door 1, door 2, and door 3. And say we choose door number 1. Let's break the doors. We go from 3 doors to 2 blocks. One block is going to be the door that you choose. All right, so we chose door number 1. The other block is the ones you didn't choose. Now, probability says, well, we get 33% chance door number 1, or that it's behind door number 1, 67% chance that it is behind door number 2 or 3. Now, when the game show host opens the doors, you cannot move the brackets. You cannot move these 2 blocks, right? They stay the same. So whether they, open door number 2 or open door number 3, doesn't matter. Say in this case they open door number 3, right? So now you only have door number 2. Now the blocks just look like this, but the percentages of the blocks do not change. There's still a 67% chance that it is behind door number 2. So you should switch. Well, the final way that I like to explain this to people is to extremify the problem. It's not a real word, but I just made it up, and I think it sounds pretty cool, so we're going to stick with it. You're going to extremify the problem. What do I mean by that? Well, let's pretend we're really rich, right? Love to pretend that. Say we have 100 doors, right, instead of 3. So let's draw that out really quick. ... 100, boom. And say there are 99 goats and 1 supercar. Let's switch it up. We pick door number 3, right? The game show host does us a massive favor and eliminates 98 of the 99 options. Say he eliminates everything else except for door 100. would you switch? Well, the reason this is more intuitive for people is, okay, they know for a fact you only had 1% chance of getting it right on door 3. There's almost no chance that you got it right on the first try. But because they eliminated so much else, well, it just makes more sense to switch, because it just seems like that would have a higher percent chance. Because, well, there's just no way you got it right on the first try. And so this would follow the logic. We could count the cases. We could break it down into 2 blocks. But this is a much easier way for some people to see that you do get a boost in percentage chance if you switch. So hopefully that was helpful. This was the Monty Hall problem. That was variable change. And have a nice day.